In this morning session, first we will go over CBL Grid. So the CBL Grid is a 2D orthogonal grid generator developed by DSI, which uses Laplace equation to create the grid. I'm not going to go over a lot of theory because you can go over and over and still forget. So the important thing is I want you to get introduced with the interface, how you can do things quickly, and we'll do an example, hands-on example for New York Harbor. It will be a simple stretch of river, and then I will build some island, and you can build on that work later. So on the screen here, this is the layout of a CBL Grid interface. On the top there are main toolbars. Some of they are like grouped together. For example, this set of tools would create splines for you. Then the ones that has grid-like structure, grid-like signs, those are used for addition of grid, deletion of grid in your domain. On the top you have this side menu where you can visualize your orthogonal deviation, and you can turn on and off grid. And on the left bottom here is a layer control. So whenever you add any new grid or spline or a DTM file, it will be loaded over here. And this is the main workspace where you will be building splines and grid. So the key features of CBL Grid are it helps us to create new grids. That's obvious. It can help you auto-orthogonalize the grids, because when you are doing this kind of numerical modeling, you need to have your grids as orthogonal as possible. It's not always possible to have this Cartesian grid in all of our models, so we need to take advantage of curvilinear grids. CVL Grid would help us do that auto-orthogonalization globally and locally depending on what you choose in the software. If you have an existing grid, it can help to edit and modify those grids. It will help to prepare grid generation support files. After you have created a grid, it can help to directly save the EFDC model out of CBL Grid. That's helpful. And CBL Grid has an option to export the grid you generated into different formats such as GRD. GRD is a native Flow3D RGF grid format. P2D is a native EFDC Explorer or EFDC Plus format. I have a link somewhere where it takes you to the EEMS knowledge base, where it has all the data structures for all the different extensions, so it's easier to have all of those referenced together. And KML file, land boundary file, and shape file. It will help to, if you don't have the grid, you can still load a EFDC model and it can extract the grid out of that model directly, and then you can edit.
So CVL can like open directly existing EFDC model.
Yes.
And so if you want to say, if I copy a model from you, I can open it with CVL, so I can get the grid.
Yeah. And if you feel like you need to add a tributary to your existing model, you can do that easily. Yeah, so you don't have to create a new grid. So any model, you can load it, and then it will plot the grid in the workspace for you. Other features that we have in CBL Grid, you can refine it. Once you create a grid from splines, you can refine it globally in I or J direction. You can make it coarsen if you want to. If you think it's too detailed, you can make it coarsened with a couple of clicks. So telescoping grid is a grid where at the start it will be a little bit detailed, and when you move further from the origin point, it will be more coarse. So you can create those kind of telescoping grids in CBL Grid. You can have a polyline, and you can drag your grid to fit that polyline exactly. You can shift by dragging your whole grid to a different location. So these are some of the files that are supported by CBL Grid for overlays. CVL extension is a native CBL Grid file. GRD, as I mentioned earlier, it's RCF grid. That's a Flow3D module. KML is a Google overlay file. P2D is a DSI file. SHP is a history shape file, and LDB is a land boundary file. And it also helps you create georeference maps. So this morning we were going to create a georeference map that you can use in your project. You can use either EFTC Explorer or you can use CBL Grid to create that georeference map. The principle of orthogonal grids. Basically, you have 4 splines or 4 lines. If they are perfectly 90 degree to each other, that's a perfect orthogonal. But if it is deviating, if it is not exact 90 degree, it's not less orthogonal. So in general, you want to make your overall grid orthogonal deviation less than 3 degrees or so, based on our model practice. And so if you can make it less than 3, it's better. The smaller the better, but in general, don't try to go over 3 because you'll have artificial numerical error in your model. So to create a new grid, there are several ways to do it. One simple way to do it is have a map on the background, so you can create splines following the shoreline and create splines out of that. Then you can generate how many I or j grid you want to create. So 4 splines are always necessary, and they need to cross each other. If they do not cross, you will get an error message. CBL Grid will give you a message of what went wrong, and you can go over and fix that. And then you can have a bunch of smaller grids, and then you can put those grids together and connect it with a couple of button clicks. You can add, delete, move cell nodes for a better grid. And as you know, this grid generation is a repetitive process, so the more you do, the more efficient you'll become at it. So this is an example of New York Harbor. So we'll be doing only the top portion. The first we'll create splines and make grids. Then at the channels, we have to create. There are a couple different ways we can do. I'll explain it later. So this on the background, this is a georeference map, and you have this overlay or shoreline, the red lines on top of the map. So this will help us as a guide. We can follow that line and create the grid, so that way we represent the topography of the study area well. So some of the common features, some of them I already mentioned, but I want to show you in figures so it's easier to understand what I meant. So the orthogonalized grids. For example, you create a grid with these kind of splines. There are splines here, and it doesn't look good orthogonal. So CBL Grid will display the orthogonal deviation as color contours. It's hard to tell the numbers from here, but it's from -81 degrees to 1.76. So you can use a global orthogonalization function, and then as you can see, with a few iterations, it will change the orthogonal deviation like this, and it looks much better than the original grid. The final average of the grid was a 0.4 for this grid, and it's good enough to run any real test or sensitivity studies. So the 1D orthogonal deviation, how it works is you have a one grid channel connected to your bigger model. So if you only want to change the orthogonal deviation on this section of grid, then you will select points in this grid and then choose to use a 1D orthogonality, and then it will go ahead and orthogonalize that particular section for you. Then refine grid, you have original grid, you have these 4 splines, and then you decide to make like 5 by 5 grid. Now if you decide to make it like 10 by 10, you just specify I want to do a global refine, and then specify the multiplier in I and j direction, and then it will create like 10 by 10 grid for you. That's pretty straightforward. We'll go over it later. So if you want to refine only one direction, so as you can see here, it's 5 on this direction, it's still 5, but we decided to increase resolution only in the I direction, so we use the multiplier, and I equals 2, it will be 10 grids in I direction, but still 5 in j direction. Similarly, the same thing for coarsening of grid. You have this 10 by 10, you want to revert back, make it 5 by 5, change your IC and JC to 2, then it will make us a coarsen grid. Coarsen grid locally, so here on j direction we have 10, and you still have 10, but on the I direction we are changing, it must have 9 or something, so we specify the divisor, how many times you want to divide, and it will divide the grid automatically for us. So this way it's much easier to do some testings. So telescoping grid, as I mentioned earlier, it will be finer at the starting point, and as you go further, it will be more coarsened. So there is a distance factor that you can play around with. The higher you choose, it will make more coarser grid towards the further point. Let's look at an example. So this is our original grid. So in order to use this function, you need to select 3 points. First 2 points will be the line, would be the points on the same grid line, and then the third point is the point, it's kind of focal point from where you want to extend your telescoping. So that would be the end point, and these would be starting. As you can see here, it is much finer over here, and it's more coarse. So if you want to have only this section telescopic, you can have your third point over here, so it would do telescoping from this point to this point. So fit to polyline is a feature if you want to exactly line up your grid with your shoreline. So you have splines for your shoreline, and you created a grid. Let's say this is your original grid, right? But you want this line to be fit with this. Then what you can do is you specify 3 points. You specify from where you want to extend your grid, and then first 2 points should be on the same grid line, and then the third point would be the point where it stretches your grid to the to the line where you want to extend your grid to. So 1, 2, and 3. So you can see up to these 2 grids, it's the same size, but it's extended in size from this. The grid size are bigger from here to here. Now if you want to make a similar size, you can just refine from this to this position, and you have much refined grid. And there is also a function called regularize that lets you have all the grids of the similar size. But remember to do run orthogonal deviation, auto-orthogonalized function after you have done all of these different functions. So shift line, it's a nice function to have, but I'm not sure if you would use it or not. But for example, if you want this grid to stretch this portion over here, so what you do is you pick 3 points as usual. First 2 points would be on the same grid line, and the third point would be the like kind of pivot where you would swing the grid. So you can see this point is still here, but from this to this portion it's stretched up to this destination point. It can be useful in some situations, but usually you would just have your splines coming in from the actual points. Yeah, that would be much easier. You don't have to manually take all of these grids. So the most important function that you will be using if you're going to use CBL grid is connect 2 grids. So I would recommend creating smaller chunks of grid and then go on building bigger from there. Don't start with it really big at first. I mean, if it's a straight channel, you can just create a whole grid at the same time. But in the much complex systems, you'll have islands, you'll have a lot of meandering going on. So it's better to create smaller grids. So here, this is a really small, simple example. But you have two sets of grid. One is blue color and one is red color. Now you want to connect these two grids. What you do is you right click on your workspace and say connect two grids. Then you just need to specify the points that are in phase to each other. So these are two grids, and you just need to specify that starting and end of that phase. You can choose to highlight this grid or this grid. It doesn't matter, as long as they are in line to each other. It will connect and then make a single grid. This is another example. Now let's say you don't want to connect the top portion, but you want to connect only the bottom portion. So you specify from this point to this point, then it will connect these two grids together and save as one single grid. Similar here, you don't want to connect top and bottom, but want to connect on the middle. Similar is just select points from this to this, and then it will merge these two grids to one. Here, it doesn't have to exactly match the exact number of grid cells. As long as they're in line with each other, they will be connected and a new grid will be saved for us. So now what we're going to do is do a hands-on for New York Harbor. So the goal of this hands-on is to have you be familiar with this CBL Grid interface, try different examples or functions that I showed earlier. So I'll show you how to load overlay file, create splines, and then we'll create a grid from these splines. We'll use the functions orthogonalize grids, connecting those grids and deleting if you think those grids are not what you think. There are several ways to delete it. You can make a polygon and then make an island right out of it. You can move the grid nodes as I showed earlier, and then refine grids. So you should be able to locate this folder under the distribution in the Dropbox. So under projects, there is a folder CBL Grid, and there should be another folder called New York Harbor USA. If you don't find it, let me know. I can copy it to a USB drive, and you can start working together. Let me go over first what we will be building, and then I'll come back together and build on like what we did yesterday. So first I'll bring this georeference map from this button over here on the top, and then you will have a map to work on. So this is our study area. If you try to make the whole thing today, it will take a really long time. So we're going to just let me load the overlay file. So we're going to create grid from this section to this. So you come a straight channel, and then there is an island in between these. So one branch coming here and one main channel, and eventually they are merging together. So we will be building this small chunk. It still requires a little bit of thinking how to do it efficiently. There are several ways to do it. We'll choose one for now and then stick with it. So the next step will be we'll create grid for the channel section. We'll create splines like this, and then we save each spline or grid just in case your model crashes or whatever happens, just for safety. I just want to save everything so you don't have to repeat it again, just in case something happens. Then you define how many cells you want in this direction and that direction. Here we chose 20 and 9. Now it creates a 20 grids in this direction, 9 grids in this direction. Then you save the grid. the native extension of the grid created by CVL Grid is .cvl. So it's shown over here. So the next grid will create new sets of spline from this point moving forward, and you'll see this spline were created and another set of grid are new grid is created from that spline. So the reason these two grids are shown in different colors because they are not connected yet. So these are two different grids. You can go over to grid and right click and format, change the color, whatever you want to do to make it pretty, but right now we're not interested on a whole lot. So now we want to connect these two grids. We just select this point at the corner and another point over here. So after you do that, these two grids will be connected and we'll have a single grid moving forward. So next it does that, then these two grids will have the same color, meaning it's a one grid. So the next we'll do is we'll create grid lines, splines on this branch. I'll say this one is a main channel and this one is a branch. So you create two grids along this channel. Then what you do is keep on building grids. There are so many things. I don't know if you want to go that. So there are two ways you can connect. So one way is this: create a spline from this point to this point right here and make a whole grid. And after you create the grid for all of this section, you just create a polyline or polygon to define this inner region and delete everything. So you'll end up having a grid that would be representative of this and this, but it is not probably going to be look pretty because if you have a spline from here to here, it will not follow exactly this smaller section. It might probably follow what's on the end. So what we're going to do is first we're going to create a grid along this branch first, and then count what is the number of grids on this channel. Let's go over it. So first we create a grid up to this point. Now it's going to this direction, so we create splines this direction. We go on finishing the grid for this branch first. You create splines, then specify how many grid cells you want. There is specified number of grids in this direction, and this grid number along this direction, and then you go on the intersection where those two grids coincide and then use the function to connect grids. Here the top portion is one single grid because up to this point we had used this connect two grids function. So there is another new grid coming downstream. Now again we connect it here. So if you want to go further upstream on that branch, you can add cells. We'll probably not do that for this example. We'll just go downstream. So we'll keep on building this grid and come all the way downstream. So after you have finished everything for the channel, then you can figure out, you can click on the cell, on the grid cell, and see your I and J index for that cell, and the end you can see an I and J index for that cell, and then from that I and J index you can find out how many cells were created on that direction, from this point to this point. This would be, for example, if it was your I direction, how many grid cells are there between these 2 points, and based on that we want to make sure we have the same exact number of grid cells over here. So if you don't have the exact number of grid cells like this, when you try to merge, they wouldn't merge. They would try to find out the corresponding points, and sometimes this grid cell at here will try to coincide with the grid point upstream of the junction. So it's important to keep track of how many grid cells you are having on this channel. And I would like to create this because it is more meandering, and you might need more refined grid over here. than this one. No, the same number from the junction here to here. Yeah. But if you don't care it's more accurate or not, you can use the first method. Just create a spline from this end of this channel to the end of this branch, and then create the overall grid, and then just delete everything. I'll show you the second, the first method. That's a crude. After we do this example, so I'll show you how both ways, but I'll prefer this because it's more detailed and you have more control on what type of grid structure you want to use in your model. So after from that previous graph, on this particular example I had 110 grid cells from this point to this point. So we create 110, we'll delete this portion, or we count this and make sure we have 110 grid cells in this main channel. So after we have the same number of grids, this red is one single grid and the green is another grid. We can connect it over here, and this will be a single grid because this face is connected to this cell and it's not connected to this point yet. So after you have these two lined up and you have created a single grid, now what we are going to do is we are going to create a new sets of grid downstream from that, and you need to make sure the number matches with the downstream. For example, if you click on this point, it will give you I and j index of that grid, and if you click over here, it will give you I and j index of that grid, and based on that how many cells will be missing here, you have to add it on the bottom cell, so it's more continuous and it's easier to connect. That's one point, but the purpose is to connect first. Similar, you can change the grid size later, you can make it refined or you can make it coarse, but in order to even connect, first this I and I index over here on the upper grid cell and the down grid cell has to match so they connect as a single grid. Right, yeah. Mm-hmm. Yeah. So after you do that, that will be the completion of this hands-on section. It's not too difficult, but we'll have to do it together, and then I'll show you several functions to use, like orthogonal, global, orthogonal, and 1D. We'll just add some random artificial branches just to play around with this example later. This orthogonalization, then I'll show you how to view your orthogonal deviation and choosing from the upper menu over here. So you can choose and you can see the orthogonal deviation is around 1 point something, and you could still keep on refining, but I would just call it good, and then I'll continue my modeling if I were to do any modeling on this study area. So if you continue to create the grid, the final grid would look like this for the New York Harbor. The final grid is available to download from my website. I think the project folder that I have provided it should still have this file, and you can play around. There are several grids in there. You can just drag and drop into the CBL grid, and it will display what grid is inside that particular file. Let's go ahead and get started now to make the grid ourselves, or chunks. So now after we create that grid, if we were to connect this smaller branch, we'll just create this section and then connect it over here, and then we'll use orthogonal 1D function to create the grid. If you want to see the orthogonal deviation of each cell, it will show you by different colors, so it's easier to say which one is more deviated and what are the cells we want to focus to. So again, this is another example. It's just fitting to this polyline. We'll extend this this portion of the grid to this polyline, use the shift fit to polyline function, and then it will fit. And then we can keep going for this. Now let's go ahead and get started. You need a 5-minute break.